Alright, so in this video we go over one more application of the chi-square distribution to test for independence. So the chi-square test for independence is used to determine whether two categorical variables affect each other. Well, that's all it is about. So for the null hypothesis, we state that the variables are independent, and for the alternative hypothesis is that the variables are not independent. That is, well, in one way or another they are related. So in this case, a contingency table should be constructed with rows and columns that describe the categories and the numbers of observations. The cells at the intersections of the rows and columns contain the observed frequencies. And then, well, so a contingency table will have R number of rows and C number of columns. So, as opposed to the previous application for the expected observation, in which we use observed minus expected squared over expected and then the sum of all of them. Well, this one is going to work a little bit different than that. So in this case, to calculate expected frequencies, we are going to use a formula: the total of row R times the total of column C, and then divide the total number of observations. So that's for the expected on a corresponding row and column. Well, so the test statistic, it's still going to be the same formula as before, well, once we gather all the data. However, the difference here will be, well, we still are going to use table A4, but for the degrees of freedom, we're going to use a different formula. Instead of the number of categories K minus 1 for the goodness of fit, what we do is the number of rows minus 1 times the number of columns minus 1. And as usual, well, reject the null hypothesis if the statistic value is greater than the critical value. Otherwise, we fail to reject. Let's look at one example. The dataset below displays the number of voters who are satisfied and unsatisfied with the current economy and their party affiliations, right? So, well, we have Democrats, affiliated to Democratic Party, affiliated to Republican Party, and affiliated to Independent. And then the number of people that are satisfied and unsatisfied. We have all the totals here and all of that. All right, so to make this, quicker and simple, I actually did these calculations. I already typed them for you, and all I'm going to do is just put the results. So for part A, we are going to calculate the expected frequency for each of the cell in the table, assuming that these two variables are independent, that is, satisfaction and affiliation. All right, so E11, what is this? E11 is the expected observation that goes from the first row and the first column. So how do we calculate those? Total of row R, total of row C over the total number of observations. I'm going to put this on the top so you can see where everything is coming from. So you might want to call this row 1, row 2, row 3, column 1, and column 2. So E11, the total of row 1 and the total of column 1. So the total of row 1, 312, the total of column 1, 305, divided by the very total of observation, which is 662. To find the expected observation for the second cell right here, which is the row 1 and the column 2, that is the expected for this guy, that's going to be the total of row 1, which is 312, the total of column 2 in this case, which is going to be, this is supposed to be a 357, silly typo here, okay, and then For now, we're gonna go with the second row. Second row, first column. So the total of row 2, which is 298, the total of column 1, which is 305. Okay, divided by the total of number of observations. And then 2, that is second row, second column. So the total of row 2, which is 298, the total of column 2, which again there's a little typo here, 375. All right. So actually your PDF should look corrected with respect to my work right here. So let's see. Now let's do row 3 column 1, row 3 column 2. So row 3 column 1, well, the total of row 3, which is 52, the total of column 1, which is 305, divided by the total number of observations, 662. Row 3 column 2, the total of row 3, which is 52, times the total of column 2, which is 357. All right, and then divide by the total number of observations. Well, in this case, I'm just going to give you the answers to these operations, but if you want to pause the video and perform these calculations on your own, well, you're free to do that. Well, here I get 143.35, 168.25, 137.30, and 160.70. And over here, 23.96 and 28.04. All right, now let's determine whether satisfaction with economy and party affiliation of the voters are independent variables at the 0.05 alpha significance level. So the whole here is satisfaction and party affiliation are independent, and otherwise, well, there's some dependence right here. All right, like I mentioned before, doing this the long way would have been it would have been a kind of a stressful task. So in this case, I have typed the values for you so we don't spend too much time doing all this. Let me refer to the table right here. All right, so in this case, we're going to have a column. The first column represents the number of rows, but row 1 has 2 columns, row 2 has 2 columns, and row 3 has 2 columns, column 1 and column 2 respectively. So what's the observed for the row 1 and the column 1? Well, row 1, column 1, the observed is 140. That is the intersection. The intersection or the observed for row 1 and column 2 is 172. Now let's do the second row. Second row, column 1, 135. Second row, second column, 163. Third row, first column is 30. Third row, second column is 22. Those are the intersection, those are the observed values. The expected values, we already calculated them at the top of this page. Now, the formula calls for observed minus expected, quantity squared, and then divide by the expected. So here I did that for you. I'm just going to explain how did I get these numbers. Well, 140 minus 143.75, I get negative 3.75. Same here, 172 minus 168, minus 168.25 is 3.75. And same here, if you do this guy minus that one, minus, you get these numbers in the O minus E column. The next column is these numbers in the previous column, square them, and you should get those numbers. And then the very last column, is the previous all the numbers in the previous column divided by the E column. For example, 14.06 divided by 143.75, that's going to give us 0.10. Same here. Oh, that's 14.06 divided by 168.25, that's 0.08, and so on and so forth. Divide this guy by that guy, this guy by that guy, this guy by that guy, and so on and so forth. At the end, we are going to obtain all these values, and if we sum them, that's 3.07, which in this case is our statistic value. All right. Well, we need to find the critical value first. In this case, what are we going to have? Alpha equals 0.05, and then pay special attention to the degrees of freedom calculation. The degrees of freedom calculation is the number of rows minus 1 times the number of columns minus 1. How many rows do we have in our contingency tables? Well, we have 3 rows. And how many columns? Well, we have 2 columns. So 3 minus 1 times 2 minus 1, which in this case is 3 minus 1 is 2, times 2 minus 1, which is 1, which equals to 2. So 2 degrees of freedom with alpha 0.05. Let's go to our table. Alpha 0.05, 2 degrees of freedom. The critical value is 5.991. All right, now observe the statistic value in this case. Well, the statistic value is 3.07. 3.07 is a number slightly less than 5.991, which falls in the unshaded region. So for this reason, we fail to reject the null hypothesis. There is not enough evidence to support the claim. So in this case, the whole wins. So satisfaction with economy is independent. It doesn't have anything to do with party affiliation. All right, so that's doing the process the very long way. And even though it's a long way, I simplified the process by just typing this so you can just follow how it is actually done the long way. So we're going to do another example, and in this example I'm going to show you how to do this using the graphing calculator. You will not have to calculate any expected frequencies or expected observations. Everything is going to be based on the chart that we have here. All right. So let's see. The data set below displays the final exam grade distribution for 215 statistics students and the number of hours the students spent studying for the exam. All right, so here we have people who studied less than 3 hours and how many A, B, and C obtained. Here we have the number of students who studied between 3 and 5 hours, and well, the number of A's, B's, and C's for students who studied between 3 and 5 hours. And then we have all the number of students that studied more than 5 hours and obtained A's, B's, and C's. All right, so determine whether the exam grade and the time spent studying for the exam are independent variables at alpha 0.01 significance level. Well, so let's see. The whole in this case is that the final exam grade is independent of the hours spent studying for it, while the ha is going to be the final exam grade is not independent of the hours spent studying for it. Well, so use table A4 to find the critical value with a statistic and compare with the statistic value. So let's find the critical value first. The critical value, which is a chi-square critical. Well, in this case, what are we going to consider? Alpha equals 0.01 and degrees of freedom, which in this case the number of rows minus 1 times the number of columns minus 1. How many rows do we have? Well, go back to the table. We have row 1, row 2, row 3. We have a total of 3 rows. Number of columns, column 1, column 2, and column 3. We have 3 columns. So 3 minus 1, 3 minus 1. So 3 minus 1 is 2. 2 times 2, which equals to 4. So 4 degrees of freedom, alpha 0.01. So let's get to table. Where did I put my table of values here? It looks like I lost my table. Oh, it's right here. All right, so 4 degrees of freedom, alpha 0.01. So 0.01 and 1, 2, 3, 4 degrees of freedom. So let's see, 4 degrees of freedom. Alpha 0.01, we get 13.277. That's our critical value. Well, actually, it looks like I got a different value. Give me a minute. No, never mind. This is fine. So 4 degrees of freedom, alpha 0.01, 13.277. So in this case, well, we are going to use the graphing calculator for this, instead of doing all that huge table. How are we going to do this? Well, you might have gone through matrices back in algebra. So we're gonna turn this data set right here into a matrix. Okay, so the matrix will be 18, 48, 16, 30, 28, 12, 33, 25, and 5. What are we going to do with this matrix? Well, so this is what we do. So let's see. Let's turn on the calculator. Quit. We're going to go second, and then the matrix by clicking the X inverse. And then in this case, you might want to edit a 3x3 matrix because it has 3 rows and 3 columns. Well, I already did it here. I already have it. Be sure to have all these numbers here. And then quit. So now we're going to go to Stat, Test, and then you're going to look for the chi-square test, not the chi-square GOF as we did before. We do chi-square test. Click Enter, and well, the observed matrix is the matrix A. For the expected matrix, you don't need to put anything. Actually, well, before we do this, let's see. Before we do this, I'm going to go back to matrix. Second, matrix. Be sure to have matrix B as one with the same dimensions as matrix A. So 3x3 and another 3x3. In this case, you don't have to put anything. Actually, if you put all zeros, that's fine. Just put all zeros. Second, quit, Stat, Test, chi-square test. In this case, observed values are the values from the matrix that we input. We don't need to worry about matrix B. The only thing we have to worry about is that they have the same dimensions, in this case 3x3. And then finally, calculate. Notice in this case you don't have to input any degrees of freedom or something. It's going to do this for you. Click calculate, and we're going to get 16.596. So using chi-square test, chi-square test, we use chi-squared equals 16.596. Alright, so if we compare this, if we put it, it's going to fall in the shaded region because 16.596 is larger than. .596. So for this reason, well, we reject the null hypothesis because there is enough evidence to support our claim. All right. So again, as you can see, it's really simple to do this test. We don't have to do through many tedious calculations. All we have to do is put a matrix A with the observations and a matrix B with the same dimension with all zeros. Actually, nevertheless, if you are curious about these values, once you perform the test, if you go back to second matrix, you want to edit the matrix, go back to the second that used to have all zeros, and it's now going to be populated with the expected values. All right, but ultimately we're not going to need them. Ultimately, what we need to do is compare a statistic value with a critical value. And this is the end of this video. I'll see you in the next one.